Hello everyone, my name is Suchandranath and my teammate's name is Saket Reddy. So for this homework we have chosen parallel processing in Erlang as our topic. So in this presentation we'll talk about Erlang at a high level and we'll cover basically all the topics mentioned on the screen, that is introduction to Erlang, history of Erlang, and basic design goals and parallel programming in Erlang, and how the performance of Erlang in multiple spaces, and about the applications of Erlang as well. So what is Erlang? Erlang is a general purpose programming language. It was built with the support mainly to support concurrency, distribution, and fault tolerance support as well. And it was initially developed by Joe Armstrong, Robert Whiting, and Mike Williams in the year 1986 as a proprietary software for the company Ericsson. And later it was open sourced in the year 1998. So it was primarily developed to handle huge number of concurrent requests in the telecom sector. And one more interesting fact about Erlang is that currently WhatsApp is developed using Erlang. Coming to design goals of Erlang, so there are primarily three goals which Erlang need to achieve. The first one is concurrency. So by concurrency here, it's the ability of the programming language to handle huge number of events occurring parallelly or simultaneously. For example, if you consider phone calls or text messages happening concurrently. So that is one of the goals. And the next one is robustness. Robustness is the ability of program to work in case of any errors, because uptime plays a key role in telecommunication or parallel processing industries. And the next one is distribution. So numerous systems are working in order to provide high availability of robustness. So now let me give some background about Erlang. So for Erlang, OTP is one of an important library. So first, what is OTP? So OTP is Open Telecom Platform. So OTP is synonymous with Erlang. OTP is a set of Erlang libraries and design principles providing middleware to develop these systems. It includes its own distributed database applications to interface towards other languages and debugging and release handling tools as well. So OTP distribution with Erlang contains an interpreter called Beam. So it basically runs on this interpreter Beam in order to compile. Now let me talk more about Beam. So what is Beam? Beam is a virtual machine at the core of OTP. It is a part of Erlang compile system. So like many other languages, Erlang source code is compiled into bytecode, which is then executed later. And unlike Jam, Beam is a virtual register machine which compiles Erlang to C first. So the main feature of Beam is that each process has their own private heap, and it works on it, and that process works on its private heap only. And Beam can also update runnable code while maintaining its state, which plays a crucial role in high availability of the Erlang. Now let me talk about Elixir. So Elixir is a Ruby-inspired language built on Erlang virtual machine. So Elixir is basically on the top layer of Erlang. So it extends Erlang macros and pipelines as well. In the recent past, the fame for Elixir has increased because of this framework called Phoenix. So Phoenix is written with the help of Elixir, and it got the fame for Erlang. Even though Erlang and Elixir are built for the same purpose, Elixir is built using large scale and low latency application. Now let me talk about architecture of Erlang. So this figure clearly shows about the architecture of Erlang. So at the low level, we have operating system which communicates with our CPU and all. And above that, there is Erlang run system along with OTP component. So both of these together helps Erlang code to compile and convert them into byte code and then to C language. And uh, side to that only we have applications in other languages. So this layer basically tells us that Erlang is flexible to work with other languages. So in real time, we have seen many applications where Erlang communicates with Java code and all. And on top of this, we have Erlang applications here as well. Now let's see how each of the design goal is achieved in Erlang. First, let's talk about concurrency. So concurrency in Erlang can be achieved by using following methods. So actor model is one of the method, and the next one is processes, and it's followed by message passing. So achieving concurrency is nothing but the ability of Erlang programming language to process multiple threads at a time. And Erlang's concurrency is considered to be very good. That's why it is being used by such a big companies like WhatsApp. Before going to different concurrency models, let's look at shared memory model first. So, using shared memory model is commonly seen in many languages, and it involves different processes accessing the same block of memory to store and communicate with each other. It's nothing but a shared block of memory. So, uh, we know that using shared memory concept may lead to some unforeseen situations like deadlocks. So to overcome these deadlocks, we use mutex locks and overcome the deadlocks. These makes the systems more complex and difficult to scale. Even the programmers find it difficult to write code using shared memory, and that's why we use mutex locks. So using mutex lock is what making Erlang follow its first design goal of concurrency. So now let's talk about the first concurrency model which we discussed in the previous section, which is the actor model. So in this model, first let me describe what an actor is. An actor is a primitive unit of computation that receives a message and does some kind of computations based on it. So communication and exchange of data among actors are ensured through message passing paradigm. An actor cannot modify other actor. So these are the properties which an actor maintains in order to make this model concurrent. So in this case, let's consider an actor as a process. So when an actor receives a message from another actor, it can do one of these things. First one is create more actors. Second one is send messages to other actors. And third one is to determine how to respond to the next message. So these are the available situations on how an actor can respond. So the messages are received in a mailbox and stored in the order in which they are received, and they are stored there until the receiving process takes them out to read. This is called asynchronous message passing. Concurrency happens because many actors can run in parallel. That's how we are achieving the concurrency.
Hello everyone, my name is Saket and from here on I'll continue the presentation. As you can see in the visual, there are three actors ABC and each actor has its own mailbox and these messages are stored in first out order and these actors use these messages to communicate with each other. In this slide, we'll talk about what are the Erlang processes and how Erlang processes are designed in a way to achieve concurrency. So firstly, Erlang processes are lightweight VM level processes and which are also known as green threads. And these processes do not map to system level process. And generally, Erlang VM creates two threads per core, one for input output and the other running the process scheduler. And these processes can act as actors and communicate using messages, as we already discussed about that. In this slide, we will talk about what are the different characteristics of a process in Erlang. And each Erlang process has a small overhead because the size of a process control block, which is also called as PCB, is only 300 bytes and it makes light in comparison to the 1024 bytes of a Unix process, and each process in Erlang has its own independent memory because each process has its own stack and heap, and the process control block of each process has these heap and stack pointers, and this method prevents memory corruption, and it's extremely important for fault tolerance. And using independent memory for each process uh, is essential to achieve concurrency in Erlang. And coming to garbage collection, since Erlang process do not share a lot of common heap, the garbage collection is on a per process basis, and it is performed by the process itself. Now we will talk about process control block for Erlang process. As we can see in the figure that each Erlang process has different parameters. For example, if we consider PID is used to determine process ID, and state is used to determine the current state of the process. And we also know that every process in Erlang has its own stack and heap memory, and so we use stack and heap pointers in process control block to map them. And it also contains other parameters like register name, spawned as, spawned by, and PC and reductions. Now let us discuss about message passing in Erlang. So basically, in order to send a message, it involves two processes, a sender and a receiver. For example, if a process A wants to send a message to process B, then the sending process A will first copy the message into a buffer, and from there it will be copied into the heap of the receiving process, which is B in this case. And each process has a queue of messages which have been sent to it and that are waiting to be processed. And this queue is maintained as a list on the heap of each process. And for example, if we consider a scenario where process A wants to send a message to process B, but process B in a suspended state, then the action of A also involves waking up the process B and adding this message to the scheduled queue. Now let us discuss about the syntax for sending messages in Erlang. For example, if we consider a scenario where process A wants to send a message hi to process B, then PID of B process with exclamation mark followed by hi will send a message to process B where the message is hi, and upon receiving the message an action will be taken by the receiving process. Here a small sample code is shown for performing different actions for different messages. So if a process receives a message MSG, then a particular action will be taken. And as we know that there will be a lot of processes in Erlang, and massive amount of messages are being sent among each processes, and so each process use pattern matching technique to filter these messages, and the delivered messages are kept until they match the receiver's message pattern. The message passing in Erlang is asynchronous because the sending process doesn't wait for the message to be delivered. And in this slide we can see the sample code for receiving process. So we can see that there are different patterns, and an action is assigned for each pattern. We can also see that there is a timeout expression used in this code. So this timeout expression is used to handle few scenarios. So to demonstrate this, let us consider a scenario where process A wants to send a message to process B, and after A sends the message to B, the receiving process B starts finding a matching pattern for the message received from A. But in some cases, the receiving process might be stopped permanently because it cannot find a matching pattern for the received message. So in order to handle these type of situations, a timeout expression is added at the end. For example, if we give 2 seconds in the timeout expression, after 2 seconds the message sent from A will be invalid and the receiving process can start processing other messages. So coming to the second design goal in Erlang, which is robustness. So Erlang is different from most other programming languages when it comes to handling errors. And the Erlang philosophy of handling errors is let it crash, which states that process cannot perform the task they were told to, should crash immediately, and another process will correct the error. So which is unlike any other programming language. And in order to achieve robustness, the system is divided into workers and supervisors. So a worker process performs all the computations required, and the supervisor process will verify whether the worker process are behaving correctly or not. For inter-process error detection, Erlang uses a special internal mechanism called as link. For example, if process A is linked to process B and process A dies, then an error signal will be sent to process B, and this error signal or exit signal will be in a tuple format. And in Erlang, a process can be linked to multiple processes, and if a process dies, then exit signal will be sent to all other processes linked to it. And in this slide at the bottom, we can also see an illustration where a process is sending its exit signal to its linked process. In Erlang, any process can trap exit signals sent by another process, and in order to achieve this, a function named process flag should be executed. And after executing this function, the process becomes a system process. And in Erlang, a system process can convert exit signals sent from another process to a message format. And like any other message, these messages are also saved in the mailbox. And at any time, the process can remove this message from mailbox and examine the reason. And depending on the reason in the exit signal, the system process might take different actions like logging an error message or sending an event message to another process or even starting a new process to replace the one that has died. In Erlang, layering of different processes is done to achieve robustness, and here in this visual we can see that different processes are layered in a tree format. And in Erlang, processes are generally divided into supervisors and workers. And in this visual, there are two supervisors to monitor the worker nodes below them to check whether the worker nodes are performing correctly or not. And also, we have a grand supervisor to monitor these supervisors as well. Dynamic code upgrade feature plays a crucial role in Erlang's robustness. And when a system availability is so critical in fields like telecommunications, taking it offline for bug fixes and upgrades is not viable. And these type of systems require special ability to push live upgrades in which the software gets modified as the systems keeps running. So this leads to zero downtime and no impact is caused. And this type of flexibility is provided by Erlang to load new and updated modules during runtime and allowing system to run without an interruption. So, and here we can see a sample code for dynamic code upgrade. So coming to the last design goals in Erlang, which is distributed. So Erlang has distribution incorporated into the language semantics and syntax, and this distribution mode is configured over TCP/IP, and any two nodes connected on the same address may communicate with each other. In Erlang, even though if a single node fails, The application still keeps running because it is distributed across several nodes. Erlang was primarily designed for achieving concurrency, and the foundation for multi-core in Erlang was the discovery of symmetric multiprocessing (SMP), and the processor in Erlang has emerged from a single monolithic run queue to a run queue for each processor. And the goal of Erlang SMP is that programmers should develop and structure their code optimally without having to worry about the internal operating system and hardware. In this slide, we can see an illustration of Erlang VM multicore. So on the left side, we have a single Erlang VM core and a run queue allocated to it. But on the right side, we have Erlang multicore. So we have multiple cores and a run queue allocated to each core. In this slide, speed versus schedulers graph is shown. On the x-axis, we have number of schedulers, and on the y-axis, we have speed up. So initially we can see that as the number of schedulers increases, the speed up also increases, but after certain point the speed up decreases with an increase in number of schedulers, and this behavior was found for both single queue and multi-queue processors. In this slide, performance comparison of process creation times is done, and we can see that in every scenario Java is taking more time in creating processes than Erlang, and after a certain point in number of processes Java gives out of memory error, but Erlang performs significantly better in creating processes. Erlang may not be suited for high-end complex computations because performing complex computations was never the goal for Erlang, as it only focused on achieving concurrency, reliability, and distribution. We can use traditional languages like Java for high computational tasks. So coming to the practical applications of Erlang, Erlang was designed to handle telecommunications, but now it is used in a wide variety of applications. And the largest development in Erlang was the discovery of ADX301 switch, which can, unlike traditional databases, the databases implemented in Erlang can store the data which is in a tree-like format, and the three most used databases which are implemented in Erlang are CouchDB, Amazon SimpleDB, and Scalaris. In the past, Nintendo Switch has sold over 34 million gaming consoles, and the system uses an Erlang-based messaging system to handle millions of concurrent connections, and even Facebook uses Erlang in their servers. And Erlang is also used in WhatsApp, Cisco, Bleachers Report, and Goldman Sachs. Finally, coming to conclusion, Erlang is primarily designed to achieve concurrency and address the challenges in the telecommunication sector. And the combination of Erlang and OTP has better advantages than traditional languages. And Erlang's way of handling errors, live code updates, and other features makes it easy for programmers to write complex concurrent programs. And Erlang is now used by many companies to handle concurrent requests. Thank you for watching my presentation.